Okay, I'll talk about universal clustering process across languages. So the primary, we are working on Indus Valley computational epigraphy, where our primary goal is the Indus Valley inscriptions. The primary goal is to development of some computational tool that can help in the decipherment of Indus inscriptions. But we know that you all, most of the people know aware that there is a limitation in the database, and also the history. There is a gap in the history of the civilization. So we don't know what happened after 1900 BC, and there is no continuity in the civilization. We don't know this inscription belongs to which current one. So there is a gap in contextual analysis. So that's why what we do comparative analysis, kind of that. We do statistical property, read statistical property of the known languages, and compare with Indus Valley in the inscriptions to understand the structure of it. So, and we have done significant work in this whole journey, and maybe you can take a talk later. But the particular talk I'm going to talk present here. So we are just trying to address this very simple question: whether Indus inscription has any syntactic structure. Why this is the question? Just because often you might have heard that somebody has already deciphered the Indus inscription, and there is some counter question. No, this inscription is not a linguistic at all. It's a random things. So we thought, being in a mathematical institute, can we prove that whether this inscription has any syntactic structure, without using any linguistic information, without using any context of the language, purely based on statistics. So with this question, we started the whole process. So we did this particular thing just based on the segmentation process. I won't explain this thing just because of interest of time. So the method is very simple. It's a kind of motif based on motif analysis, where we are saying that if a subsequence of the given sequence, if the joint probability of the sequence is higher than its random chance, then we can say that it's a significant subsequence. And based on that, we have done that. I'm just ignoring the whole process, and we finally got this kind of segmentation. So each highlighted part is the segment, which what we can say significant subsequence. The result, our method is producing in terms of what's called the binary tree, the full binary tree. So the unique thing is here, if your given sequence has lot of recurrent structure, so then so your binary tree will come up like a perfect binary tree, and that you can quantify. And if your sequence is completely random, it will come up in this way. It's just full binary tree, but it's not perfect. The quantification you can done here. You can quantification done very easily just by looking at the height of the tree, which is here. If it is perfect binary tree, it will come up as in log of n with base 2. Here is the n minus 1. So what we found that all these empirical language sequences is showing the height is somewhere in between in these two extreme end, while the random sequences is here. So in this way, we at least managed to establish that this particular inscription is not at all a random inscription. It is lying somewhere with the empirical sequences. This is one thing what we introduced. But when we deep down in the study further, then we thought, what is these particular segment corresponding to? Then we found that mostly these are the either root words or some kind of affixes, whether it's a prefix, suffix, infix, you can say that. So these are around 40% are the affixes. Rest are some other sequences. Other segments. So the point is, then we went a little further, and then we found that what is the simple question we said? What is the simple distribution of those segments? Then we found that it showing a special case. Is a power law with exponent of 1, which is Zipf's law. So and we know that in linguistic, Zipf's law has a as a specific meaning. Well, it is just in a rank order things. But don't focus on the what's called statistics of it. It's not. It's a closely related because significance is not that great, but it's closely related, which at least can tell you one thing, that it's saying that the small set of your segment is playing a lot of role, is playing plays significant role in the word construction, while rest of the segment are less in use, rarely in use. So and then when we went further, so then we went further to just know that, okay, what kind of what are the required number of segment we need to construct a word. So what we found is a completely unique thing, that irrespective of the language you're talking, a writing system you're talking about, the average number of segment you required is on an average 3. You can see the distribution. It is irrespective, though the variation of number of primary segment, primary grapheme it uses in different languages is very high. So this is what we found very unique property, is a kind of we already checked in around 25 languages, and this is a universal property we found. But still, we don't know why this kind of things are appearing. That is still an open question. So, so the point is, so at least based on this study, we established at least one thing, that our method is introduced a segmentation method, which is managed to identify the recurrent segment of a linguistic sequences, which provide a specific approach to study the sequence, which is a structure approach. And the second thing is that, okay, due to closeness of the Zipf's law, it indicates that a systematic uses of those patterns, those segment in the language construction. And this third one, what I said, that the consistency in the universal pattern, what we have found, that to construct any word, you need on an average 3 segment per word. So again, I'm saying that, okay, why this universal property, we don't know. Maybe is it because of some cognitive constraint plays a role here, which is saying that, okay, the cognitive that universal cognitive constraint reflecting the inherent human preference, which leads to this kind of numbers, or phonotactic, or whether phonotactic constraint, whether we're saying that the arrangement of the sound, because we know that XY is not very common, but YX is not common. So whether this kind of sound arrangement plays some kind of a role to restrict some boundaries, or even there is a possibility whether the acoustic limitation, whether the anatomical position, the condition of our vocal cord, which may lead this kind of limited numbers. So these are anyway still the question. So yeah, this kind of work we do. Thank you.
Any questions?
I remember an early study about DNA sequence.
Yep.
Thinking about it as a language. There is some message, and trying to study correlations and long-range order and so on. I remember they can distinguish species. Human DNA will have something. Cockroach will have some other parameter. So I wonder if there is any connection of your study with.
Okay, okay, I'll tell you in this way. This is you can say that even if you are saying this particular, vaguely. So if you will see, if you will use those kind of text into the segment or method, the height, it will just appear somewhere here. So even if you see that the synthetic data are having some kind of small motifs, but that won't, somewhere it will lie here in this boundary. So it's managed to distinguish from the boundary. I haven't used that slide, so it is just because because of the time constraint. So yeah, so those kind of sequence won't easily filter out. So yeah, so that.
What is the typical line segment length for the Indus value script versus all the other?
So that is at least typical length is 5 to 6. The longest what I am using is 14 only.
And it is very different from the languages which you have deciphered, which are deciphered.
No. See, that's why in terms of this particular study, that's what I'm saying, that the bandwidth, because all language is somewhere coming in between in these two limits. And most of the empirical language is lying somewhere in between. And even surprisingly, even the Indus is in that region. So that's why I was saying that, okay, Indus showing the similar syntactic structure or at least inherent structure what known language is showing. That you can say that, okay, it doesn't mean that it's language or not language, at least I'm telling you that's a syntactic structure.
But then since you don't have a Rosetta Stone analog of it, so you can't decipher it still.
Okay, very recently I met with the Mark, me and as a process and met with this guy, Mark Canoyer. Even I asked the same question. Even he said that same thing, that okay, without Rosetta Stone we can't do that. But I don't agree fully, because we can do a lot of things. Even by the same method, we have successfully managed to decipher at least recognize the directionality. We didn't use any inherent grammar or anything, just based on statistics. What we did that okay, just the distribution of terminal distribution. We did it. Even we have one of our study is, so that is, we matched it. And there is another study we have done, kind of the classification of the whole sequence, the scenery, where we are saying if a person tomorrow want to write the grammar of this language, they should focus in this section. Because every language has some kind of general rule, some exception. So we have managed to do it. So there are a lot of questions can be done. So even linear B is one of the example which is done without Rosetta Stone. So I cannot claim, but yes, we should not be hopeless. Sorry.
Yeah, just a comment to Shayantan's
Yeah.
thing. So, like he already mentioned, linear B is a wonderful example where you deciphered, Ventris deciphered it without a Rosetta Stone. Another is Mayan. Mayan hieroglyphics were deciphered without having a Rosetta Stone. But in both cases, actually people guessed what could be the nearest living language be. In the case of linear B, it was Greek, and in the case of Mayan, it was Maya Quechua. Quechua was still being spoken. And for the actual Rosetta Stone, even with the Rosetta Stone, Chapolet would not have been able to decipher unless he had guessed that that language must be closely related to Coptic. So I think more than the Rosetta Stone, what one needs to do here is kind of make a guess as to what could be the nearest living relative language. That will be the real clue.
But I read somewhere that in Mesopotamia there used to be trade links.
Absolutely. So
They have some exchanges, so it's not possible to get some.
So it's very interesting you say that. So in fact, for a long time, there was this hypothesis known as Dravido-Elamite, that the Dravidian and the Elamite, which was spoken in Susa in Iran and so on, actually form one single language family. And there's still a lot of work carried out on that genre, but nobody has yet been able to work out from that guess what this could mean. Yeah, but it's one of the things that people are working on.
Okay, so let's thank the speaker again.